Well, I would like to thank Professor Yu for the invitation to this workshop. And next, I feel very honored to give a talk in front of Professor Bangbang, who after so many years since I took a math course from him as a student. Okay, the title of my talk is Integration with respect to vector measures and Lyapunov convexity theorem. From my attending yesterday's lectures, I found that my subject is a little bit off from the main track of this workshop, so I decided to spend less time on my own result, and most time I'm going to explain the basic stuff so that you don't feel bored. Okay. By the way, this is a joint work with my previous PhD student, Dr. Lee. First, I will introduce what vector measures are, and then perhaps you are familiar with this Bartle integral, but I'm going to define this integral. And then, as a generalization of Bartle integral, I will explain this new integral, Lewis integral, and I'm going to show you a characterization, namely when my function is Lewis integrable. Okay, and then the main topic of this talk is convexity of the range of vector measures. Okay. Okay, so let's get started with the first concept of vector measure. So, in order to talk about vector measures, okay, so I'm going to use this letter M. First, I need a measurable space. So this large sigma is a sigma algebra on this set, and then a Banach space. Then my measure is going to be a set function from sigma to x. Okay, not arbitrary set function, but the ones countably additive. Okay, so today I'm going to just treat countably additive vector measures. So countable additivity is, of course, if you have a disjoint sequence of measurable set with union E, and then this measure is summation measure of En. And by this I mean the norm E minus n equal 1 to capital N En. This norm tends to capital N, tends to 0. Okay, this is what I mean by countable additivity. So in the special case when x is say r, R, this is nothing but the signed measure. Okay, if you happen to have the range of m to be 0 to infinity, and then this is a normal measure, the usual measure, finite measure. Okay, so but okay, I will consider in general Banach space. Okay, so if you have, say, two signed measures, okay, something like this, two signed measures, and if you define m this way, you get a vector measure. Okay, and you can generalize this to n-dimensional case. But if you define a vector measure this way, this is not always countably additive, even though its component set functions are measured. Okay, you can easily check when this is L infinity value, the countable additivity amounts to saying these measures are uniformly countable additive, and you can find example of sequence of measures which is not uniformly countable. Okay. Before I move to the next section, I want to introduce you some basic facts. The first fact I want to use is every vector measure is bounded automatically. So when I say vector measure, it is countably additive. Okay. Bounded means this: you have a non-negative number, so that this norm is bounded by m for all e. Okay. All e, if you can find such number. Perhaps you are familiar with this in case x equal r. Okay, so if you have a real valued signed measure, it is automatically bounded. You can easily see this if you decompose, if you use a Han decomposition like a positive set and negative set, and then any general E, okay, any E can be broken into two parts, right? So E is less than E intersect P plus E intersect, and then I think the actual value is this. Anyway, and this is of course less than the whole P, and so this can be your M, right? But this is without using Han decomposition, you can show countably additive. Okay, this vector measure is bounded. It can be a good exercise for your student. Okay, because I'm not going to explain the details of two. Perhaps I can sketch the one way of checking this for arbitrary vector measure. Okay, so this is the idea. When you have a vector measure, always, okay, suppose M is not bounded and you get contradiction, okay? If it is not bounded, you can find a measure of set E and its complement so that the norm is greater than 1 and the M omega prime, let me use A here. This is unbounded. Okay. If my vector measure is not bounded, then I can find a subset where it is still unbounded, but the rest has a measure greater than 1. Okay. So this is the first step, and it's quite easy because you can find the E such that because it is not bounded, this is greater than 1 plus. Okay, this is some fixed positive number. So if your measure is not bounded, there exists E. Okay. So this is the picture. If this is the whole omega, you call the complement F. Okay. So by additivity, you have this is measure of E plus measure of F. Okay. So I have this minus measure of E is equal to measure of F. Let's see which way I want to, let me walk the other way, okay? And then, by triangle inequality, this measure is less than, because this is difference of this, omega plus M. But this norm is greater than this, so 1 plus norm of omega. So when you cancel this measure of omega, you find that this norm is also greater than 1. So both parts has a norm. This is all greater than 1, right? So assuming my vector measure is unbounded, I have a decomposition and such that each part has a measure greater than 1, okay? Okay, and here you consider this. Two collections. Say E intersect A, where A is from this, and F intersect A from A. Okay. And at least one should be unbounded. If both are bounded, then every A can be broken into two parts. So you see the measure M is bounded. Okay, so if this is unbounded, I use this E, and F is going to my omega prime and so on. Okay, so this is a simple step. After this, what you do is first time you get E1 and omega 1 with this, okay? And then when you consider your vector measure only here, it is unbounded. So again, you can find the E2 and the rest omega 2, so that E2 has a measure greater than 1, and your vector measure is unbounded here. You just keep going, okay? What you have here is then you get disjoint. you get disjoint sequence of measurable set so that each one has no greater than 1. And this gives you contradiction because by countable additivity, you must have this identity holding. In particular, this sequence of vectors, okay, converges. That means that the nth term should go to 0, which is impossible by this inequality. Okay, so perhaps I covered two basic things, but okay. The second part is called Bartle. Stanford. It appeared in their paper, Schwartz. Okay. Every vector measure has a control measure. A control measure. What is the meaning of control? Nu is a finite measure, and it is absolutely continuous, which means this is 0 whenever mu of E is 0 for every E, okay? So this is absolute continuity. Okay. So I'm going to use this facts freely. But the second part is a little bit deep, so I'm not going to touch the detail. Now, Bartle integral, okay? So our setting is as before. And so M is a vector measure. Okay. Everybody agrees that if you have such characteristic function, then the integral must be E, right? So if I have a simple function, so here f is a function of a real valued function, okay? This is what I'm considering. Then naturally, you want to define this integral this way, and this is Banach space value. Now one can easily check this is well defined. So here, when I write my simple function this way, EI's are disjoint. Okay, this is well defined and linear. Okay. Actually, one can check this is bounded also. This linear functional is bounded if I give f the supremum, okay? So in this case, supremum is nothing but the maximum. And then I can check the integral. Twice, if M is an upper bound for my vector measure M, so it is bounded. Okay. Okay. I will show this simple inequality. So in order to check this, I'm going to hit when this is less than 1. I'm going to hit here. And I will show this is less than actually this quantity. That's enough. Okay. because the norm is supreme of this stuff. And so if I hit x star here, because x star is linear, I have x star here, and you find AI x star MEI, I is 1 to n. So I break here, then this is the maximum of this. So I have I is 1 to n, x star m, EI. Okay. I will write this sum into two sums. I is, say, I plus, and I is I minus. I plus means when this is positive, okay? When I collect, eventually, because this is linear, I have x star, and here I have then union EI, sorry, and x star. I have this stuff. And yeah, actually exactly this. Anyway, same thing as this. This is less than, because the norm is less than 1, this is less than m of this stuff. And m was my upper bound, so I have the same thing with the second sum. So this is bounded. This is pretty much all about Barty integral. And I have a few remarks about this. First, I haven't used the countable additivity of n except the boundedness. So this argument works if m is just additive and bounded set function. Okay. The second remark is, as you might have expected, this simple functions, is a subspace of bounded functions, bounded. If you use all bounded functions, so this bounded linear functional can be extended to the closure of a simple function space. So the conclusion is I can still talk about this integral when f is in the closure of a simple function space. In other words, if f is uniform limit of simple functions, I can talk about this Bartle integral, and still I have such inequality. Okay. But anyway, my f is bounded. Okay. So the question is, can we have some sort of integral when f is unbounded? Okay. So this is one possibility, namely Lewis integral. Here, the f is again always real valid, measurable. Okay. Then I say, we say that f is integrable in the sense of Lewis if two conditions hold. First, here, the absolute value. By the way, if I apply bounded linear functional, this is a set map from to R. And this is a signed measure. In other words, this is still countably additive. So you can think of its variation measure, and this is a finite measure. And if this Lubin measure is finite, okay, for all x star, and this is first condition. The second condition is for each measurable set, there is x, you might call x of E, in the Banach space such that when you apply x star, this is same thing as applying x star here. So this is a signed measure, and because of first condition, this makes sense. Okay, again, Lebesgue measure for all x star. Okay, so this is a definition of Lewis integral. This vector is denoted by our integral. Okay. Then the first observation is if M happens to be the real valid or best, this integrability is nothing but Lebesgue integrability. Okay. The second observation is if f is a simple function as before, then simple function is Lewis integrable, and the integral, as you might expect, is the same as Bartle integral. Okay, this is easy to check. The third one is suppose f is integrable. Actually, with respect to m. In this case, if you look at this Lewis integral, this is actually a set-valued function. So you can define another set-valued function this way. And it turns out that this n makes another vector measure. Namely, it is countably additive. Okay. So I'm going to explain a little bit more about this last one. Okay. So how do I check countable additivity? When E is decomposed into sequence of measurable set, I need to check this is equal to okay. You remember what I mean by this, right? This is but the series converges to this one in the Banach space, okay? Here, the first thing we are not sure is whether or not the series, okay, converges. Okay. If I can confirm that the series converges, okay, to some vector x, I can easily check that vector should be exactly this vector. Why? Because I can apply x star both sides. X star, okay. Well, because this is countably additive, I have x star m en, n is 1 to infinity, okay. And because this one converges to X in the norm topology. It converges in the weak topology. So I get this is X star X. Okay. If this is X, then when you apply continuous function X star, you get this identity. Okay. So they have same value for each function, so they are the same. Okay. So the main thing is why this series converges. Okay. For this, we use a classical result in Banach space called Orlich-Pettis theorem. Orlich-Pettis theorem says when you have a sequence in your Banach space, okay, this is the assumption. For each n1, n2, okay, so x and k is a subsequence, right? For each subsequence, there is x such that you have this summation x star, x and k is 1 to infinity is equal to x star x. This is what they call weakly subseries summable, okay? This is for all x star. Conclusion is then the series converges. Okay, so let's try to check summability of our series using Orlich-Pettis. So this is my xn in the application. So suppose I have a subsequence, okay? So what is the candidates? What is candidates for the weak sum of this? Well, obviously the x is e and k is 1 to infinity. This is the candidate. So what I want to check is when I hit x star, I want to check this is equal to x star m union e and k. This is all I need to check, right? K equal 1 to. And that's obvious because this signed measure is a signed measure of countablative, okay? So whenever I have a subsequence, okay, this one, okay, weakly summable to this vector. So by the Orlich-Pettis theorem, the sequence converges. So that is all I had to check. Okay, I erased the definition of Louis' integral, but one result we got is the following characterization theorem. This is measurable. The following is equivalent. Okay, f is integrable in the sense of Louis. The second, there exists a sequence of simple functions such that first For simple functions, this integral makes sense. The limit exists for each measurable set E. And next, there is a small set E, such that f and omega converges f of omega if it is outside of this small set. So you can say it converges almost everywhere. By small, I mean this. E is small if the measure is 0 for all. Okay, this is smallness here. I'm not going to touch the technical argument here, except that in the proof we make use of the criteria for weak compactness within such Lebesgue space for positive measure. Okay, namely, a collection is relatively weakly compact if and only if it is absolutely, uniformly integrable. Okay, I use that. And also for scalar version, I use scalar version of Vitali convergence theorem. And finally, I use Rybakov control measure. For a vector measure, you know, there exists a control measure, okay? If mu takes this special form, we say it is a Rybakov control measure. Rybakov proved every vector measure has a Rybakov control measure. I use such facts, but yeah. The statement is the following are equivalent. Sorry. Okay, finally, this is the last section of my talk, last part. Convexity of the range of vector measures. Convexity. This is a classical Lyapunov. There are many other ways of spelling his name. Lyapunov convexity theorem, okay? This is 1940, what's it? 1940 or 40? I think 1940. If okay, M, you can write it this way, right? Is a non-atomic vector measure. Then the image, okay, or the range is convex. It is compact. It is compact and convex. In application, convexity is more important. Non-atomic means each component signed measure is non-atomic. When I say mu1 is non-atomic, that means this positive measure is non-atomic. And this positive measure is called non-atomic whenever this is positive, okay, you can divide it into two parts so that each of them has positive measure. That is definition of this is non-atomic. And this has an important application in optimal control theory, so-called the Bangbang Principle. Okay. This is a finite dimensional convexity theorem. If I had some time, maybe I will have a chance to justify this, but if not, let's see. This is called this was generalized to Banach space case by Null. Okay, let M be a vector measure with a control. Every vector measure has a control measure, okay? In this setting, the followings are equivalent. First, okay, you look at the image. Let's see, what do I use? EA. This time, not compact, but weakly compact convex for all E. Okay. So in particular, when E is the whole space omega, you get a convexity of this range. Second, whenever mu over E is positive, there is a bounded measurable function such that this is non-trivial. This is not zero function in L infinity. That means this function is not equal to zero mu almost everywhere. It's not. But still, the interesting thing is it is balanced in this sense. Okay, this is a zero vector. By the way, if you don't remember much from my talk, perhaps you can still remember this application. Application of Lyapunov's theorem. Okay, I might call it a dividing problem. Dividing problem. When I was young, my brother and me shared many things. When, say, my mother bought a rice cake for me and my brother, we used this rule to divide the cake. Okay, first we had the rock and scissors, and we choose one. Okay. If my brother won, then I'm in bad situation, but not perfectly, because I divide the cake. After I divide the cake, my brother first choose. Okay, this is, in a sense, a little bit fair, right? Everyone has different eye. Some people think this is, suppose they have same area. Some people say this has a larger area. Some others this. Even if they have perfectly same shape, the cake on other people's hand looks larger, right? We have such problem in Korea. Okay. So everybody has a different measure, okay? So in this measurable space, we have, okay, a probability, non-atomic probabilities. Okay. So there are n people, so there are n probabilities. Non-atomic means, okay, this. When you think this exceeds more than 1/2, at least you can pull out a little bit, take off a little bit. The same thing as non-atomicity, okay? So in this case, there exists measurable partition E1 En of omega, so that Pi Ei is greater than 1/n, which means everybody is satisfied, okay? The whole cake can be divided into n parts, and the first piece, okay, I give it to the first person, second piece to the second person. They think they got at least the proper amount, at least, okay? So everybody is happy. This is possible, and I have done this for n equal 2, and n equal 3 was, I used induction, but it was very complicated. And I don't know how to generalize it to n equal 4. But if you use Lyapunov's theorem, you can get solution this way, okay? What you do is this. You define vector measure this way. At empty set, this is the value, right? The whole set, the value of m is 1, 1, 1. So these are in your range, okay? Because this is convex, okay, this is one convex combination, right? And the result is this. I know this is also in the range. What does that mean? There exists a set E so that P1 of E to Pn of E, this vector equals this. That means at least for this piece, everybody thinks its measure is 1/n. Okay, so this. And what about the rest? The rest, everybody thinks the measure is this. Okay, now you use, okay, this vector. So the proof is by induction. Okay, so this is not a probability here, but by scaling, you can make this one a probability space, right? And so by the assumption for n-1, you can decompose this to En-1 so that everybody is satisfied. What about this one? Well, give it to the nth person because he is also satisfied already, right? So this is the cake dividing problem, and that's an application of Lyapunov's theorem. Okay. The second result I want to explain is this theorem. So this is the setting. F is integrable. Okay, F is integrable. In this setting, if this M E intersect A is weakly compact convex for all E, then the same thing holds for N. This is a weakly compact convex for E. Okay. This is actually a simple application of this, so I'm not going to give the detail, but for the rest of 5 minutes, I'm going to give you some feeling why at least this direction holds, or why this is a generalization of this. Okay. Okay. First, why is this a generalization? So the problem is in this setting, okay, can I check this condition for my vector measure, right? And then in particular when E equal omega, I have convexity. And also for in finite dimensional case, compactness is equivalent to weak compactness. So that's what I have. So give me, in order to apply this theorem, I need a control measure. Okay, for my vector measure, this is a control measure. Okay, if this measure is 0, every measure is 0, so M of E is 0. Okay, so suppose this is positive. Okay, that means at least one of this is positive. Say mu1 is positive. I know this is non-atomic, so this E can be broken into two parts, so that mu1 of E1 is positive, and same thing for the second piece. And do you see this? Yeah, because is sum of positive quantities. And also E2 is positive. Well, precisely speaking, this is positive. Again, you divide this one again and again until you have n plus 1 pieces with positive measure. Okay? Here, I need to construct G. My G is going to be A sub I, characteristic E sub I is 1 to n plus 1, okay? I need this condition. G times characteristic E is same thing as G times characteristic just G, because everything is within E. Anyway, this is non-zero if and only if some AI is not 0, okay? So every piece has positive measure, so if I can find G where some AI is non-zero, and also at the same time I need this, okay? This is the same thing as what? As E, G, D, mu J is 0 for every J, right? In this case, the integral you can check is same thing as a componentized integral. It's easy to check. So you wanted this, okay? But what is this? When you apply this, mu J of EI, again, E is a superset of this, so you don't need to consider this. AI summation, I is 1 to n plus 1. you need to determine AI so that each of this is 0. But I have only n many equations, n plus 1 variables, so I have non-trivial solution. Okay, so I have a solution where some AI is non-zero. This is all, right? When you check B implies A, what you do is this. First, you consider this. The F in L infinity such that, okay, this is basically open ball. The closed, this is basically such closed ball translated by how much? Translated by 1/2, right? Here. Constant, if you add constant 1/2 function, get this. So by Lyapunov's theorem, which says in the dual space, the closed unipole is weak star compact, right? That's in the dual space, the closed unipole is weak star compact. So this is a weak star compact. And also, obviously, convex, right? Okay. And then I apply integral to this set. So I have this F. The integral F is W. So for F, I apply this function. I know this is linear, integral is linear, but it has nice continuity. The integral is weak star to weak continuous, which means whenever this converges to F in the weak star topology, the integral converges to this weakly. Okay. Yeah. Actually, yeah. The reason is, that's a good question. This is almost everywhere bounded, measurable. So by the basic facts, it is the essentially uniform limit of simple functions, right? And that's why. So when you check weak convergence, you need to test this. But by definition, this is same thing as X star here, right? X star. Okay. In this setting, the M is controlled by mu. So obviously X star M is controlled by mu. So by Radon-Nikodym theorem, this is okay. You have Radon-Nikodym derivative, okay, in L1 of mu. Okay, so this is same thing as what? D. Okay, this is same thing as GD mu, also GD mu. But where is G? In L1, the pre-dual of L infinity. So this follows from weak star convergence. Weak star means that when you hit G from L1, you have convergence. So the image is this time weakly compact and convex. Okay, this is weakly compact and convex. And the image, the range of measure is surely contained here because the M of E is nothing but characteristic E, the M, and this function is here, right? So if you can check these are equal, you are done. Actually, I am doing this, the case when E equal omega. Actually, that's enough, okay? So how do you check this? Okay, so you pick any vector from the right-hand side, okay? And what you do is you form a set here, K, F from W, so that the integral is again x naught. It's same thing as this. This is part of W, and because this is Weak continuous. Let's see. Yeah. So this is again Weak-Star compact convex. Okay. So by the classical theorem by Crane-Millman, it has an extreme point. Okay. It has an extreme point. Extreme. And you can check f should be actually a characteristic function. Otherwise, you will have trouble with this assumption. Okay. Maybe I should stop here because the time is over. Thank you.